Artificial intelligence is now pervasive in all sectors, such as industry, healthcare, finance, and logistics, and its close interdependence with climate change has been demonstrated. On one hand, numerous applications of artificial intelligence can help reduce the effects of climate change in the sectors where it is adopted. At the same time, AI is also one of the applications that most affects the environmental impact of IT. Its growing adoption leads to a significant increase in computational demand, resulting in impacts on the energy consumed and the greenhouse gas emissions of data centers. It is estimated that in the last 10 years, the computing power required by artificial intelligence has increased by about 300,000 times. According to some recent estimates, the AI sector as a whole could, in the next decade, consume a significant share of the energy available for IT, contributing to a non-negligible increase in global CO2 emissions, if not properly managed. This situation highlights a fundamental dichotomy. On one hand, AI is an emerging source of energy consumption, especially in large-scale models. On the other hand, if designed and used consciously, AI can significantly contribute to reducing emissions in many areas by improving the energy efficiency of processes. The issue of AI's environmental impact has led to the introduction and comparison of the opposing concepts of red AI and green AI. The term red AI refers to an approach focused exclusively on maximizing performance, often at the expense of energy efficiency. These systems tend to prioritize metrics such as model accuracy, ignoring the computational cost required to achieve such results. In contrast, green AI aims to develop machine learning models that optimize not only performance, but also energy consumption and environmental impact. Green AI, therefore, proposes a more sustainable approach, which includes reporting the energy used and employing efficient models. Among the AI models with the greatest impact are deep learning models, a subcategory of AI that uses deep neural networks, or DNNs, as predictive models. The learning process requires numerous interactions and can last many hours or even days, using high energy consuming hardware. These models are widely used due to their proven effectiveness, but they have a significant environmental impact. This impact is influenced by multiple factors, which can be divided into two main categories: model-centric and data-centric. The most relevant model-centric factors are the type of architecture used. There are many different architectures that can be employed to generate a model. Studies have found that the choice of model significantly affects the energy consumption required to generate it, the number of parameters in the model. The parameters of a deep learning model are the numerical values that the model learns from the data during the training phase, and they determine how the model transforms input into output. In large models, the parameters can number in the billions, as is the case with large language models. More parameters correspond to a greater capacity to represent complex relationships in the data, but also to higher computational costs and an increased risk of overfitting. The number of training experiments needed to fine-tune the parameters. In addition to deciding the number, training an artificial intelligence model also requires specifying optimal values for these parameters. This phase, called hyperparameter tuning, is the most energy-intensive part of deep learning because it involves training numerous models with different configurations to find the one with the best performance. The infrastructure used for training, the type of hardware on which the training is performed, and the energy mix that powers the infrastructure both contribute to determining the consumption and the environmental impacts. Taking these factors into account, the energy impact can be reduced by using lightweight and efficient architectures, decreasing the number of parameters used in the models, and employing knowledge distillation techniques that allow the knowledge of a complex model to be transferred to a smaller model. Another relevant perspective regarding the environmental impact of AI is related to the data used during the training phases of the models. It is well known that the size of the training set used to train an AI model has a significant impact on the quality of the resulting model. However, this affects the computation time required to generate the model. From a data-centric perspective, the factors that have the greatest impact are the volume of the dataset. Large datasets are essential for improving the accuracy of deep learning models because they provide a greater variety of examples, helping the model to learn general patterns instead of merely memorizing the initial data, thus avoiding overfitting. However, endlessly increasing the amount of data does not lead to unlimited improvements. After a certain point, the gains in accuracy tend to diminish, while computational costs rise. For this reason, it is important to find a balance between the size of the dataset and the efficiency of the model, also from the perspective of energy sustainability. The quality of the dataset. Noisy or redundant data can lead to computational waste. At the same time, noise in the data is necessary to prevent the resulting model from suffering from overfitting, that is, being too precise in representing the data used during the training phase, but unable to generalize to data not seen during that phase. The data preparation phase is fundamental in the AI lifecycle to prevent incorrect results and biases caused by poor quality data. Some studies have analyzed the effect of data quality on various machine learning models, considering aspects such as completeness, accuracy, consistency, and class balance. From this perspective, it is possible to reduce the environmental energy impact of AI by decreasing the volume of datasets used for training, finding the right balance between model accuracy and computational costs, and using data cleaning techniques to provide the model with cleaner datasets. Although in this lesson, we are mainly focusing on the energy impact of AI and the challenges related to its consumption, it is essential to remember that artificial intelligence can also be a valuable tool for promoting sustainability. Numerous examples, in fact, show how AI can concretely contribute to reducing energy consumption and emissions in various sectors. In the energy sector, for example, AI can optimize the management of smart grids, balancing supply and demand more efficiently and better integrating renewable sources. In transportation, advanced algorithms can plan more efficient routes or manage traffic intelligently, reducing congestion and fuel consumption. Agriculture also benefits from these technologies thanks to precision farming, which allows for the use of only the necessary amount of water or fertilizers through accurate and targeted forecasts. Finally, even within the IT sector itself, artificial intelligence plays a dual role. On one hand, it contributes to increasing consumption due to the training and use of models. On the other hand, it is used to make data centers more efficient, for example by improving cooling or optimally distributing workloads, with a direct impact on reducing overall energy consumption. The growth of artificial intelligence presents new challenges in terms of energy sustainability. The environmental impact of training complex models can no longer be ignored. However, by adopting a conscious approach through green AI techniques, monitoring tools, and optimization strategies, it is possible to effectively balance performance and environmental impact. At the same time, AI can be part of the solution, directly contributing to the ecological transition of other sectors as well as IT itself. To truly make the use of artificial intelligence sustainable, we must design and adopt it carefully so that its innovative potential translates into tangible benefits for the environment and society.